Hello everyone, hope you are doing well. Welcome to the online platform Civil Technobricks. Guys, here we will tune for instantaneous decoding of conceptual knowledge in the field of civil engineering, where study elaborates decoding the earth to build a better world. Today we will go through the core concepts related to the differential GPS, that is DGPS, based on principles, error correction and engineering applications. Guys, DGPS is an enhanced GPS technique which utilized to improve positioning accuracy using a reference stations, or we can say that the ground control points. It corrects common GPS errors and provide more reliable coordinates. The system of DGPS which compares known and measured positions at a fixed station, where the calculated corrections are transmitted to mobile receivers. So DGPS is widely used in engineering survey, mapping and high accuracy point of view, where infrastructural projects and its surveying is corrected. Its objective is to reduce errors because that errors caused by atmospheric conditions and satellite inaccuracies. So DGPS works by using a fixed base station that transmits correction signals to mobile receivers, where it provides higher accuracy which compared to the standard GPS. So DGPS is the advanced version of standard GPS. Key characteristics for that DGPS which include error correction and enhancing the reliability on it. So for the civil engineering point of view, it is crucial for high precise work or high precision surveying like road alignment and bridge construction point of view. We can use the DGPS for the precision work. So precision gap in engineering survey, where autonomous GPS and differential GPS. So standard limitation for that autonomous GPS, where autonomous GNSS measurements suffer from inherent atmospheric and orbital errors which are limiting accuracy of nearby to the 5 to 10 meters. But for differential GPS, the engineering requirements are on the basis of site specific analysis which requires sub-meter accuracy, where the property boundary mapping demands centimeter level precision. Means that standard GPS which provide accuracy of about 5 to 10 meters, where the level of accuracy is insufficient for engineering projects. But for the DGPS, that significantly reduces positioning errors which provide sub-meter to centimeter level accuracy, which depends on the method of its usage. So the precise positioning is essential for construction layout and monitoring point of view, where the accurate coordinates improve the quality and safety. What are the sources of positioning error? So sources of GNSS positioning errors, basically we can say that the GNSS measurements are affected by satellite, atmospheric and receivers error. So satellite errors, signal propagation and local receiver errors. So there are two types of errors, where signal propagation, which is the path where medium is required, that is ionospheric or tropospheric conditions. So the ionospheric and tropospheric delays alter signal travel times. This results in incorrect distance measurements from satellites, where the multipath reflections and receiver noise which introduce additional errors. That DGPS is designed to minimize these all common errors and their sources. So here the satellite errors are clock bias and ephemeris errors, where local receiver errors are the receiver noise and multipath errors. These are all the sources of GNSS positioning errors. Moving towards the concept of the reference station, that is precisely known coordinates, that is XYZ, means a reference station is installed at a precisely known location where its exact coordinates are already established through accurate surveys. That station is continuously receives signals, satellite data. It compares measured positions with its true known positions or true ground control points. So basically, the reference station, which is a stationary receiver located at a surveyed point of absolute truth. So the role of that reference station is that continuously monitors signals from all visible satellites, which compares the measured GPS position with reference to the known physical position and attributes the difference to systematic error mitigation or calculation. So the difference represents the positioning error These corrections are then supplied to nearby users. The working principle where the base station and the rover observe the same satellite simultaneously. Therefore, they experience nearly identical satellite and atmospheric errors. So the base station and the rover plays important role with reference to the n number of satellites at the same time. The base station calculates correction values in real time data or scenario where these corrections are transmitted to the rover receiver, where the applying the correction improves positioning accuracy. The rover obtains much more reliable location estimate based on the assumption that is spatially corrected or spatially correlated errors on the basis of atmosphere and orbit error. So that satellite 1 is connected to base station and rover at the same time, satellite 2 and satellite 3. Likewise, the each and every data will be corrected on the basis of n number of satellites from the rover and its movement. The error correction point of view, the mechanism which is divided into three parts. First will be the measure and compare, second one generate correction, and third one will be the apply to rover. Means where measure and compare, the base station receives satellite signal and it calculates difference between measured range and the known range. That is the measure and comparison in between the both station. Where generate correction means we have to calculate the error by the measured value minus true value, where the correction factor computed for each satellite, and at the end we have to apply to the rover, where rover receives that correction, where the subtracts error from its own observation to refine its actual position. Means that correction values are generated continuously and the information is sent to rover receivers through communication links. That rover applies the corrections to its observations. This significantly reduces common GPS errors. So result is compensates for clock bias, ephemeris errors and atmospheric delays common to both receivers. Moving towards the real-time scenario, that is the real-time kinematics, or we can say that the real-time differential positioning. What is meant by the real-time workflow required? That is base monitors satellites and calculates error corrections. Base broadcast message via UHF radio or cellular link frequencies, where rover receives GPS signal plus correction message. And fourth one, that is rover computes accurate coordinate instantaneously in the field. Means that real-time kinematics is an advanced real-time DGPS technique. On the basis of that technique, the real-time workflow will followed or calculated or conducted, or corrections are transmitted instantly from the base station to the rover station. Here the carrier phase measurements which provide centimeter level accuracy, which makes real-time kinematics more suitable for engineering grade survey. So the real-time kinematics is widely used for construction staking and alignment work, where engineers can obtain precise coordinates directly into the field. So what is the use case of that real-time differential positioning? For the navigation purpose, for the real-time mapping and the stakeout activities. Next one will be the post-process DGPS. So post-process DGPS means after the data collection work. That is in post-process DGPS, the correction is performed after field data collection, where the raw observations from the base and rover are proceed in the office. On that condition, no real-time communication is required during the survey. So it makes the method suitable for remote locations and feasible to the village areas also. So post processing which improves survey accuracy significantly, so that it is frequently used for mapping and geospatial projects. So the methods for that post processing of DGPS are the corrections are applied retroactively after the mission or the data collection, where workflow is followed, that is rover collects raw observations back into the office. We have to use that software download reference data from a permanent base station and recalculates the position with reference to the ground control points. So what is the advantage of that post process DGPS activity, which is highly reliable and no need for live radio line of sight? The accuracy, most important point, that is improvement hierarchy. So accuracy which is based on some autonomous GPS, code based DGPS and carrier phase DGPS. So this is all about related to the distance point of view. Autonomous GPS for navigation grade, code based DGPS for mapping and GIS grade, and carrier phase DGPS is for surveying and engineering grade. So autonomous GPS generally provides 5 to 20 meter accuracy. This is sufficient for basic navigation applications. Code based DGPS, which improves accuracy to less than 1 meter. It is commonly used in GIS and mapping locations, where carrier phase DGPS and real time kinematics, which achieve 1 to 5 centimeter accuracy, which is utilized carrier wave cycle counts for extreme precision. These methods are preferred for engineering and cadastral surveys. So accuracy is most important for that purposes. A wide area of DGPS and SBPS, satellite based augmentation system and differential global positioning system. So satellite based augmentation system use a network of ground stations, that is ground control points, to calculate a continental correction model, which is broadcast to users via geostationary satellites just like VAS, IGNOS, GAGAN and MASAS, where DGPS performs decreases, or we can say that the DGPS performance decreases as the distance from the base station increases. So the error correction or error correlation becomes weaker over larger baselines. Here, multipath reflections are most important and they can still affect positioning quality. So that the building, trees and terrain features often causes signal reflections, so that the error will be in that data. So clean line of sight to satellite is more essential while taking the data. So obstructions we have to reduce, or we have to take the data without any obstruction, so that the satellite visibility and survey accuracy will be easy and clear. Moving towards the application, with reference to a surveying and photogrammetry point of view, DGPS provides accurate ground control for mapping of projects, which improves the spatial accuracy of geospatial datasets, where direct georeferencing is conducted with reference to GPS. That GPS provides the coordinates with reference to X, Y, Z position of the camera center at the moment of exposure. The drone and aerial photogrammetry surveys use DGPS for georeferencing, where accurate positioning reduces the need for extensive ground control points. The engineering surveys benefit from precise coordinate measurements, where project planning and design become more reliable and efficient, which means that efficiency which reduces the need for manual ground control points and the property mapping applications. With reference to hydrographic application, that is radar is most important, where DGPS is widely used in hydrographic survey and coastal surveys also, with the accurate positioning which improves water depth and shoreline measurements. Marine mapping, which requires precise vessel positioning, where that DGPS ensures reliable navigation during survey operations. Where ocean bathymetry, coastal mapping, these are all the applications with reference to the hydrography, where X, Y and Z, that is elevation, which is also taken for the consideration. So coastal monitoring and bathymetric studies depends on accurate coordinates with reference to the high quality and spatial data improves engineering analysis. So the DGPS link, which is used to measure the sea height, the position of the sensor itself must be known perfectly. The system limitations, that system limitations are based on the baseline distance, multipath distance and line of sight distance. So here we see that the satellite based augmentation system provide regional DGPS corrections, for example like VAS, IGNOS, MASAS, GAGAN, so that these all corrections are transmitted through geostationary satellites basically, and the users who receive that signal, which improve the positioning accuracy over large regions. Means here, the baseline distance, multipath distance or line of sight, these are all the system limitations for that wide area of DGPS and SBAS. So the baseline distance for correlation of atmospheric errors, which degrade as distance increases. Next one will be the multipath, that is DGPS, which cannot correct for local reflections uniquely to the rover's environment with reference to the obstruction. And third one will be the line of sight, that is clear line of sight is most important, so that which requires clear view of satellites, that is urban canoids or buildings and heavy canopy block signals, as explained in the picture. Stay tuned guys, happy learning.